So today's lesson is about mutually exclusive events. And so what we're really talking about with mutually exclusive events is we're trying to figure out if we want certain events to occur, or we have an event, we need to figure out if, if we have like two or more events, what we're trying to figure out is if those events have any outcomes in common. And so if we think back to set theory, we're looking at or questions here. So we're looking at like this event or this event happening. And whenever you have or, so in just taking a step back, in math, looking at set theory, A or B is written as that A union B, and it's said to occur if the event A occurs, or if the event B occurs, or if both events occur. And whenever you have or, remember or means you're going to add. Okay? And so when you see that intersection or that union, that means you're dealing with or you're going to do some sort of addition. Tomorrow we're going to look at events A and B. So when you want like that sort of intersection is what we're looking at there. When the event that you're looking for is that intersection to occur. And when that happens, when you have and, then that means you're going to multiply. Okay? So for everything we do today, we're strictly doing adding. Okay? And let's just remember that the probability of an event is equal to the number of favorable outcomes, or number of outcomes favorable to the event, divided by the total number of outcomes. Okay, so we'll do a quick little investigation to sort of illustrate the difference between mutually exclusive events and non-mutually exclusive events. So when you have a question where you have one thing happening or another thing happening, so where that event will occur if A happens or if B happens or if both happen, you have to determine if those events A and B have any outcomes in common or if they're mutually exclusive. So we're going to look at the experiment of rolling a die and noting the result. Okay, so that's our experiment, is rolling a die. Event A is going to be an even number, and event B will be an odd number. So we can mark these events, or the outcomes of this experiment, in a Venn diagram. So A is our even number, so the even numbers on a die, remember the universal set for this would be 1, 2, 3, 4, 5, and 6. Right? We have 6 outcomes. So for event A, even numbers, we have 2, 4, and 6. And for event B, odd numbers, we have 1, 3, and 5. Okay, and so we're just going to answer some questions about this. Notice in the Venn diagram there's no overlap in there. There's no number that is both even and odd at the same time. So the outcomes for event A are what we've put in the Venn diagram for event A, so 2, 4, and 6. The outcomes for event B are what we've put in set B for the Venn diagram, is 1, 3, and 5. The event A union B, so A or B, that's the same as the universal set. So that's what we listed up here. So that's 1, 2, 3, 4, 5, and 6. And the event A union, or intersect B, right, which is the intersection, there's nothing in common, because the intersection implies that there's that overlap, right? If you have the intersection, that's that part in the middle where both, where the events overlap. So that's the, for this particular experiment, A intersect B is the empty set. And remember, when we put the n in front of something and we have the event in brackets, then that means we want the number of outcomes in that event. So the number of outcomes in event A is 3, and the number of outcomes in event B is 3. The number of outcomes in A union, or A union B is 6, and the number of outcomes in A intersect B is 0. So if we know that our total number of outcomes in the universal set, right, so that the universal set has 6 outcomes in it, that's the same as A intersect B, we can use that to figure out the probability of rolling an even number, the probability of rolling an odd number. So the probability of rolling an even number, the probability of event A, is 3 outcomes, so there are 3 even numbers that you can get out of a total of 6. Okay, and I'm not going to put that in lowest terms. I'm going to leave it as 3 over 6. Same thing for event B. The probability of rolling an odd number, you have 3 odd numbers out of a total of 6. So really your odds, or your probability for both events is 0.5. For A union B, there's 6 outcomes, and there's 6 total outcomes if possible. So this event is certain to happen. Right? When you roll a die, you're either going to roll an A or you're going to roll a B. And the probability of rolling an odd number, sorry, you're either going to roll an even number or an odd number. The probability of getting a number that is both even and odd at the same time is 0, because there are no numbers that are like that. Because in this experiment, the events A and B have no outcomes in common, then that means they're mutually exclusive. And in the Venn diagram, when you're talking about mutually exclusive events, there's no area of overlap, right? The sets A and B are disjoint. There's nothing that that overlaps between them. And so what we're going to do is just verify some stuff here. We're going to look at that these two expressions hold true. So the number of outcomes in A intersect B, which is 6, should be equal to the number of outcomes in A, which is 3, plus the number of outcomes in B, which is 3, and that equals 6. So that's true. The probability of the union, so A or B, is 6 out of 6. The probability of A is 3 out of 6. The probability of B is 3 out of 6, which gives a total of 6 out of 6. So this is true. Okay. So we're going to look at non-mutually exclusive events now, investigating non-mutually exclusive events. So now what we have in this case, notice we have, we've got this, the intersection for the Venn diagram is evident there. So now we're still going to look at the same experiment. We're rolling a die. A is an even number is thrown, and B is a multiple of 3 is thrown. Okay. So I'm actually going to change this. I'm going to do B first for events A and for B, so we know how to maybe to fit in our Venn diagram. So event A is an even number, so that's 2, 4, and 6. Event B is a multiple of 3, so that's 3, which is 1 times 3, and 6, which is 2 times 3. So we can see they have one outcome in common. Okay. And we'll use that to fill in our Venn diagram here. So we have 2 and 4 and 6 in A, and we have 3 and 6 in B. So then the event A or B is everything in the Venn diagram. I'm going to just put, we've got 1, 2, 3, 4, and 5 are in the outside there. And our universal set is still 1, 2, 3, 4, 5, and 6. That doesn't change. So A union B is everything in the two circles in the Venn diagram. So 2, 3, 4, and 6. And A or B, or A and B, sorry, the intersection is the 6, which is in, this means what's in both. And this is in either. So the number of events, or number of outcomes in event A is 3. The number of outcomes in event B is 2. The number of outcomes in A or B is 4. And the number of outcomes in A and B is 1. And I'm just taking that from the sets that I've written there. So then the probability, the total number of outcomes in each case is always 6. Okay, we're always over 6. We have 3 possible outcomes for event A, so the probability of event A occurring is 3 out of 6, or 1/2. We have 2 outcomes for event B, so the probability is 2 over 6, or 1 over 3. The probability of A or B occurring, there's 4 outcomes in A or B, so that's 4 out of 6, or 2 out of 3. And the number of outcomes of A and B is 1 out of 6. In this particular experiment, because you've got that overlap in the Venn diagram, then that means these events are not mutually exclusive, because that means that there are some outcomes in both. So that has to come into effect, or that, so you have to take that into account when you're finding the probability. And if you remember back to the unit assignment on the Perms and Combs unit, there's a question about cards, right? And it was, I think, like hearts and kings or something like that. And you had to take off the one that, like, you couldn't count the king of hearts twice. You had to take it off. It's sort of the same thing. Okay? And when you have that overlap, when you've got an area of overlap in your Venn diagram, which represents A and B, then that means set A and set B are not disjoint sets, and you have to account for the probabilities a little differently. So we're going to verify that the number of events in A or B, which is 4, equals the number of events in A, which is 3, plus the number of events in B, which is 2, minus the number of events in A and B, which is 1. So that gives you 5 minus 1, which is 4. So that's true. We'll do the same thing for probability. We have 4 over 6. Probability of A is 3 over 6. The probability of B is 2 over 6. And then we're going to minus off the probability of A and B, which is 1 over 6. So we have 3 plus 2 is 5 minus 1, 4 out of 6. So then that is true. Events are said to be mutually exclusive if they have no common outcomes, and if the probability of A and B occurring at the same time is 0. And that leads us to 2 formulas. Okay, so we have 2 formulas, and both of these formulas are on your formula sheet. So both of these are on your formula sheet. What you need to do is recognize when to use each one. So if you have events that are mutually exclusive, which means if you draw a Venn diagram, there's no gap or overlap, the sets are disjoint, then the probability of A or B happening, because that's what that union means, A or B occurring, is just the sum of the individual probabilities. If you have a situation where if you were to draw a Venn diagram, you have an overlap in the middle, so you have an intersection that exists, then you use the same formula except for the fact that you have to subtract off the probability of A and B. So you have the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And then this formula also works backwards. You can determine if an event is mutually exclusive or not if you have these probabilities and you figure it out. If the probability of A or B just equals the sum of the individual probabilities, then your events are mutually exclusive. If not, then they're not mutually exclusive. So we'll just start with an example where we are trying to identify logically whether an event is mutually exclusive or not. So we have an experiment, a die is rolled, we have event A is an even number, event B is an odd number. This is what the investigation we did at the beginning. These are mutually exclusive events. A card is drawn from a standard deck. We have a face card, which would be Jack, Queen, King, but there's 12 of them, one of each suit, or a club is selected. So there is a Jack of clubs, a Queen of clubs, oops, my drawing is not going so well here, that's a Queen, and a King of clubs. Let's try it this way, like this way. Anyway, so these, because we have face cards that are clubs, these are not mutually exclusive. 2 dice are thrown. The dice both show the same value, so that would be 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So basically you're rolling doubles. Event B, the total score is 11. So if we add these, can we get 11? If we have 2 of the same number, there's no way we can get 11 because 11 is an odd number. And when you add the same number to itself, you're always going to get an even number. So these are mutually exclusive. Mutually exclusive events in A, an even number and an odd number, they're complementary events. If you have complementary events, they will always be mutually exclusive because they have no events in common, but the opposite isn't true. Mutually exclusive events are not always complementary. So complementary is always mutually exclusive because they can't happen at the same time, but vice versa is a little bit different. So again, we're going to look at identifying mutually exclusive events. So we've got 5 different events here. We've got event A, a face card is selected. A red card is selected for event B. Event C, a club is selected. Event D, an ace is selected. Event E, a black card is selected. So we want to know which pairs of events are mutually exclusive. So A, a face card. So is there any way to get, let's see, a face card. Face cards can be red, so those aren't mutually exclusive. A club can be a face card. An ace is not a face card. So A and D are mutually exclusive. A face card and a black card, you can have black cards that are face cards. Okay, A red card is selected and a club. Clubs are black, so A and B are mutually exclusive. A red card and an ace is selected. And you can get an ace that's a red card, so those are not mutually exclusive. A red card and a black card are selected. Those are complementary, so those are mutually exclusive. A club and an ace we can get. A club and a black, those are not mutually exclusive. An ace and a club we can get at the same time. So these are only 3 sets of mutually exclusive events. And of these pairs which are complementary, that was event A, or event B and event E. Those are complementary. And we'll look at yet another example of how we can represent mutually exclusive events, or events, and determine whether they're mutually exclusive. So to be mutually exclusive, there needs to be no overlap. So A and B, B and D, A and C, A and E and D. And I think that's it, right? Because B and C aren't mutually exclusive, and C and D aren't mutually exclusive. Now we're going to actually work with formulas here. So we want to use the given information in the probability formula to determine whether events A and B are mutually exclusive. So what we want to do is we want to find if we can, we want to figure out which formula actually works here. So the probability of A or B should be equal to the probability of A plus the probability of B if these events are mutually exclusive. Not mutually exclusive, then we would have to subtract something off at the end. A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So let's try this. Let's try the first one. So 1 over 4 plus 1 over 3. Okay, we need a common denominator, so let's make that 12. So that becomes 3 over 12 plus 4 over 12, which is 7 over 12. And since this equals the probability of A or B, then that means these events are mutually exclusive. If you added the probability of A to the probability of B and you got a number different than 7 over 12, then that would mean they were not mutually exclusive. Okay. A card is drawn from a standard deck of 52 cards. We want to use formulas to determine the probability that we have a 9 of diamonds or a heart. So if this is event A, a 9 of diamonds, and event B is a heart, then we know the number of events in A, 9 of diamonds, there's 1 card. The number of events in B, a heart, there's 13. And 9 of diamonds is not a heart. So these are mutually exclusive. So what we have is the probability of A or B is equal to the probability of A plus the probability of B, which is we have 1 out of 52 cards is a 9 of diamonds, plus 13 out of 52 cards for the heart. So that gives us 14 out of 52, or in lowest terms, 7 out of 26. A 9, or a heart. So if event A is a 9, there are 4 9s in the deck. Event B is a heart. There are 13 hearts. And there's 1 9 of hearts. So there's 1 card that is in both. It's both a 9 and a heart. So these are not mutually exclusive. So the probability of A or B is equal to the probability of A minus the probability of B, plus the probability of B minus the probability of A and B. So 4 cards out of 52 for hearts, or for a 9, plus 13 cards out of 52 for hearts, minus 1 card out of 52 for the 9 of hearts, which gives you 4 plus 13 is 17, minus 1, 16 out of 52, which will simplify to 4 out of 13. So that's how you use the formulas to determine the probability. And we'll look at another situation that's quite similar. We have a single bag in which we have 3 cubes, 1 blue, 1 red, 1 green, so there's 3 there. Let's just keep track of that. There's 2 pyramids, 1 red and 1 yellow pyramid, and there are 5 cylinders, 1 blue, 1 yellow, and 3 red. So that's 5, so we have a total of 10 shapes in that bag. So sometimes it's helpful to go through, like I've done in the previous example, and determine the number of outcomes in each event before determining the probability. So a pyramid or a cube. So in terms of, if we call, let's call cube, let's call pyramid A and cube B. So the number of outcomes in event A, which is a pyramid, are 2. The number of outcomes in event B, which is getting a cube, is 3. And you can't have a pyramid that's a cube. So these are mutually exclusive. So the probability of A or B is equal to the probability of A plus the probability of B, which is 2 out of 10 plus 3 out of 10, which gives you 5 out of 10 or 1 out of 2. Okay, so not red. We want the probability that the cube will not be red. So that means that event A, so let's say what we're looking for is not red. I'm going to make that event R prime. So not red means everything else that isn't red. So we have a blue, green, yellow, blue, yellow. So that means there's 5 cubes that are not red, because we have 1 red plus 2 reds plus 3 reds is 5. So the probability of not red is 5 out of a total of 10 cubes, which is 1/2. Red or a cylinder. So the nature of this experiment, we had shapes that were colors. So 2 different shapes, you can't have anything that's mutually exclusive. 2 different colors, you can't have anything that isn't mutually exclusive. But if you have a color and a shape, you might have something that's both. So red is going to be, we'll say that's event R, and cylinder, we'll say that's event C. So the number of red shapes is 1 red cube, 1 red pyramid, 3 red cylinders. So there's 5. And the number of cylinders is 5. But the number of objects that are red and a cylinder, we've got 3 red cylinders. So the probability of A or B is equal to the sorry, not A or B. Let me fix that. So we have the probability of R or C is equal to the probability of R plus the probability of C minus the probability of R and C. So for red, we've got 5 red shapes out of 10. We have 5 cylinders out of 10, and then we have 3 objects that are red cylinders. So 5 plus 5 is 10, minus 3 is 7. So probability of getting a red or a cylinder is 7 out of 10. You could have also just added it up. Well, how many cylinders do we have? Sorry, how many red things do we have? We've got 1, 2, 3, 4, 5. And then we have a yellow cylinder and a blue cylinder, so 6, 7, and that would give you 7 out of 10. So depending on how the experiment's set up, sometimes it can be quite easy to determine the probability. And we'll do one more example. It's a little bit more complicated. Tom and Andrew were asked to solve the following problem. 200 people with neurology symptoms, which include headaches, backaches, and backaches participated in a study to evaluate a pain relief medicine. All the people took the medicine, and the results were as follows. 60 people experienced headache relief, so we're going to call that event H. Okay. So then the probability of event H is 60 out of 200. 126 people experienced backache relief, so we're going to call that event B, and the probability of B is 126 out of 200. 36 experienced relief from both, so this is the probability of a headache and backache being cured, and that's 36 out of 200. What is the probability that a person who takes the drug experiences relief from at least one of the two symptoms? So what that means is H or B or both. Okay, neither of the symptoms is going to be neither a headache nor a backache. So that's going to be headache or backache and then prime. So that's the complement. Tom decided to solve the problem using a probability formula, and so we're just going to complete his work. Now, I wrote this up top, but let's just put it down here. So probability of B is 126 over 200. The probability of H and backache, so H and B, is 36 out of 20. So we want at least one. So that at least one is the OR. So the probability of H or B is equal to the probability of H plus the probability of B minus the probability of H and B. And I'm going to actually go up here. Let's put in some decimals so that we're adding decimals instead of fractions. So 126 divided by 200 is 0.63, and 36 divided by 200 is 0.18. So probability of headache is 0.3, probability of backache is 0.63, but there's 0.8 in common between the two. So 0.3 plus 0.63 minus 0.18 gives you 0.75. And I took up all the space for part 1. That's what that was. So let's just go over here. Part 2, we want the probability of not H or B, right, like that. So that's just equal to 1 minus 0.75, right? It's the complement of the event in part 1, which is 0.25. Andrew decided to solve the problem using a Venn diagram. So we're going to complete the Venn diagram. We've got the 36 in the middle. So remember that this means that, like, we had 90 and the number of outcomes, the number of favorable outcomes for H was 60, and the number of favorable outcomes for B, for backache, was 126. So to fill in the Venn diagram, we have to take off the amount that might be in the middle. So this gives you 24 for headache. And we're going to subtract off 36 here, which is going to give you 90 for backache, like that. Okay. And that means there's, if we add this up, 24 and 36 is 60 plus 90 is 150, so that means there's 50 that are outside. So then, for the first part, we want the probability of A or B, or both. So that's going to be, so the probability of A or B, or both, is just 24 plus 36 plus 90 over 200, which gives you 24 plus 36 is 60. So 150 out of 200, or 0.75. For the second one, for part 2, neither of the symptoms, then that's the number that lies outside the Venn diagram. So the probability of not A or B is 50 out of 200, or 0.25. And that's mutually exclusive events. So your assignment is a worksheet that's attached to this notes booklet, and it's questions numbers 1 to 12. And if you want some extra practice or some different types of questions, then you can go to the textbook. And just give me a moment here, I'm just looking it up because I didn't write it down. And that would be in the textbook, page 176 to 180. Numbers 1 to 17. So just if you're finding this stuff in the worksheet a little easy, look for some more difficult questions. Okay, and that is today's lesson. Do some work, make me proud, work well for the sub, and the next video will be on Monday.